Hi there, welcome to this video, lesson 6.6, and we're going to be talking about integration with inverse trigonometric functions and advanced integration techniques. Now, when integrating a fraction where the degree of the numerator is greater than or equal to the degree of the denominator, we're going to need to do long division in order to split the fraction. Okay, and if you just wanted to go ahead and try U substitution or reverse chain rule, you'll find out that this doesn't work and it doesn't account for all the terms. So what we need to do in this case, notice that the degree of the numerator is the same as the degree of the denominator. So we're going to go ahead and do long division. So I'm going to take my denominator, x squared plus 2, and I'm going to divide it into my numerator, x squared minus 4x plus 2. Okay, so x squared goes into x squared one time, and if I go ahead and multiply these, we get x squared plus 2, and my remainder, after I switch my signs, negative, negative, where these cancel, I now have a negative 4x. So this is minus 4x over my denominator, x squared plus 2. Okay, so I can go ahead and rewrite this integral as the integral of 1 minus 4x over x squared plus 2. And all of this is with respect to x. So our first integral is not a problem. We know that the integral of 1 is x. And here, I'm going to go ahead and integrate for this fraction. I'm going to use the u prime over u form. So the integral of u prime over u is the natural log of u. Okay, where in this case, my denominator is my u, my x squared plus 2, and the derivative of that is 2x dx. Okay, so I can go ahead minus the integral of, I need a 2x and a dx. So I have 4, so I'm going to pull out the 2 out front, and I have over x squared plus 2. Okay, so here is my reverse hook that's going away, and I have x minus 2 times the natural log of x squared plus 2 plus c. Okay, and there is integration using long division in order to be able to put it in an integratable form. Here is example number 2. Now, example number 2, if I was going to go ahead and do long division, that would not get me anywhere. So what I'm going to do is I'm going to use u substitution, and I'm going to let u be equal to the square root of x. So therefore, u squared is equal to x if I went ahead and squared both sides. And therefore, if I took the derivative, 2u du is equal to dx. And I'm just going to go ahead and make some substitutions here. So this is equal to the integral of, I have, instead of dx, I have 2u du. So you can see this here. So 2u du over, in the denominator, I have u instead of square root of x, and then minus 1. Okay, so now this is an integratable form where I can go ahead and I can do long division in order to be able to integrate this. Because notice the powers, right? U to the first over u to the first. I need to go ahead and do long division. So I'm going to integrate, or sorry, not integrate, I'm going to divide. So u minus 1 divided into 2u, and this occurs 2 times. So 2 times u gives me 2u, times negative 1 gives me negative 2. And if we go ahead and change our signs and then add down, we get a remainder of positive 2. So this is plus 2 over u minus 1. Okay, so this is equal to the integral of 2 I like to just go ahead and split my integral right away. So I write it like this. So plus the integral of 2 over u minus 1 du. Okay, now the integral of 2 du is just 2u. And here I have a straightforward natural log integration, right? My denominator is u minus 1, and the derivative of that is just 1. So plus 2 times the natural log of u minus 1 plus c. All right, where I now need to go ahead and substitute back. So this is equal to 2 times the square root of x plus 2 times the natural log of the absolute value of square root of x minus 1 plus c. Okay, and there you have it. That's using long division in order to be able to integrate. Alrighty, so now I'm going to go ahead and introduce integrating arcsine forms. And I'm going to start off going back to the derivative of arcsine is 1 over the square root of 1 minus u squared times the derivative of u, which is u prime. So we can move that into the numerator, as well as our arctan form. The derivative of arctan is 1 over 1 plus u squared times the derivative of u, which is u prime. So that's why you see u prime in the numerator. So it makes sense. It makes sense that these would be, the reverse of these would be our integration rules. The integral of u prime over 1 minus u squared dx is equal to the arcsine of u plus c. And the integral of u prime over 1 plus u squared dx is equal to arctan u plus c. Again, where u is a function of x. And we're going to go ahead and extend these because we generally see this format, right? In the denominator, I have a square root of 1 minus u squared, okay, or something squared. That tips us off that it's arcsine. Or if I don't have a square root, right, and it's 1 plus something squared, that tips us off that it is arctan. Well, you're not always going to see the beautiful number 1 in front. Sometimes you may see another number. Well, the good news is that we do have an integration formula for this. So here is the main form that you're going to use, and notice it's exactly the same, except instead of a 1, we have an a squared down here. So notice here, instead of 1, it is a squared. So notice the same format, right, of arcsine. But now when we integrate, when I have an a value other than 1, our solution is arcsine of u over a. So we just divide whatever the argument is by the value. And we'll see an example here in a second. Plus our constant for indefinite integrals. All right, and then I have the same idea here. If I have an integrand where I have u prime over a squared plus u squared dx, where again, I don't have a pretty nice clean 1 in front of the a. I have some other number or some other value. Our solution is going to be 1 over a, so I divide by that a value, times arctan, again, of u over a plus c. So I would put these on some flashcards. I would memorize these, be able to easily recall them. Not a question mark, exclamation point. So we can go ahead and use those, okay? And then again, maybe you're saying, hey, what about arc cosine? Where the heck is arc cosine? Well, remember, the derivative of arcsine and the derivative of arc cosine only differ by a negative. So it's not necessary to have the third integration rule, which utilizes arc cosine of x. We can just always pull out the negative as a multiplier, okay? So you'll never see the arc cosine pop up. All right, so here is kind of a warm-up example to kind of show you that a value that we were talking about. So here they say differentiate arcsine of x over 2. Okay, so this is sine inverse of x over 2. All right, so if I want to go ahead and integrate this, this is y prime is equal to, okay, the derivative of arcsine is 1 over the square root of 1 minus whatever this argument is here. So I have 1/2 x, and that is squared. Now I also have to take the derivative of the inside, which is 1/2 x, so that is just 1/2. Okay, so I'm going to go ahead and rewrite this as 1 over 2 times the square root of 1 minus, now 1/2 x times 1/2 x gives us 1/4 x squared. Okay, and what I'm going to do in order to show this, to put this in the format that we want, is I'm going to suck this 2 into the radicand. And in order to be able to multiply them, I'm going to change that 2 to be a square root of 4, right? Because I can go ahead and I can multiply square roots and just distribute that 4. So I have 1 over, so 4 times 1 gives us 4, and 4 times negative 1/4 x squared is just x squared. All right, so there you have it. I have just differentiated this format, and I'm in this form. Now our next solution is going to go ahead, our next problem is going to go ahead and have us integrate this, the same exact answer, and we're going to arrive back at our original problem here. Okay, so that was differentiation. So now let's go ahead and integrate. All right, so number 3, I want to integrate. All right, so just looking at this, right away in your head, you should say, hey, this is sine inverse form. I see the square root in the denominator. I see 2 perfect squares where x, right, is the u value, and then the a value out front, right, is 2. Let me go ahead and rewrite this so you can easily see that. 1 over the square root of 2 squared minus x squared dx. Okay, so our integration rule says that this is equal to arcsine, or sine inverse, of u over a. So x divided by that first value, x over 2 plus c. And that is it. Very, very straightforward. Okay, let's go ahead and look at example number 4. And with example number 4, you should be thinking, this looks like tan inverse form. We have 2 values squared in the denominator. So here, this is 2x squared. That is our u value, 2x. And if I have a u that is a function of x, we have to account for u prime, which is 2. And we also have an a value here, which is 5 squared. So a is equal to 5. Okay, well, notice I don't have a u prime. I don't have a 2. So I'm going to have to introduce the 2, and then I'm going to have to balance it. So balance it with the 1/2. Okay, and if I go ahead and integrate this now, so now I do have my 1/2 that comes along for the ride, times, and I'm going to have to use my tan inverse integration rule, which is here. So the integral of u prime over a squared plus u squared dx is 1 over a. Arctan of u over a plus c. Okay, so 1 over a, which is 1/5. Tan inverse of u over a, so 2x over 5 plus c. And there you have it. If you want to simplify that to 1/10, be my guest, but you don't have to. All right, example number 5. Here we have a definite integral, and again, we are looking at a tan inverse form. So I have here square root of 3 squared. Okay, so that's your a value. And then again, I have 2x squared here. So u is equal to 2x where the hook column factor, the reverse chain, is 2. Okay, so notice I do have an 8 in the numerator, right? This 8, we're going to turn this into 4 times 2. So the 2, there's your chain, it's going to go away, and we can pull a 4 out front. So let me just go ahead and rewrite this so you can easily see. So 4 times the integral of 2 dx over the square root of 3 squared plus 2x squared. And this is integrated from 0 to 1/2. Okay, so I'm going to go ahead and integrate this. So this is equal to 4 times, actually, I have a value, so I gotta include that. 1 over a, which is square root of 3, times tan inverse of u over a. So that is 2x over square root of 3. Okay, and I'm integrating from 0 to 1/2. All right, so let's go ahead and evaluate. This is equal to 4 over the square root of 3 tan inverse of 2x. If I plug in 1/2, 2 times 1/2 is just 1. So I get 1 over square root of 3 minus, again, 4 square root of 3 tan inverse. If I plug in 0, 2 times 0 is 0. 0 divided by anything is just 0. So there we have it. And we want to go ahead and evaluate this. Tan inverse of 1 over root 3. I'm just going to go ahead and make a right triangle here. If this is tangent, tangent is opposite over adjacent, root 3. So this is 2 up here. And this is going to be, we know that this is 90, right? This is a special right triangle, 30, 60, 90. And again, 1 or root 3, this is going to be our 30-degree angle, and 60 is going to go here, right? Because the smaller angle goes to the smaller side. So I know that this is pi over 6. So 4 root 3 times pi 6 minus tan inverse of 0 is 0. So this just goes to 0. And there you have it. All right, so here is a practice problem. Please go ahead, pause the video, try this example, and then evaluate. All right, hopefully you pause the video and try this example. Here is the solution. So you had a u value that is 3x. You had an a value, which is 5. And you had to go ahead and introduce a 3 and balance it with a 1/3. So you should have gotten 2/3 times 1/5 tan inverse of 3x over 5, evaluated from 0 to 5/3. Now, when you plug in 5/3, that just gives you 1, which tan inverse evaluated at 1 is pi/4. And then if we plug in 0, again, tan inverse of 0 is 0. So there is your answer. All right, this is the last set of examples I'm going to have for this video, and then I'll finish up the rest of the lesson in a second video. And what I want to point out, at least for the next 2 examples, is that these problems are similar, but our approaches are different. So I just want you to let you look at these and kind of notice, okay, what's the difference between the 2? And actually, this one was similar to the one that we just did too. So if you look at example number 5, you'll notice that the only thing is changing is we're increasing the powers, okay? So example 5 was tan inverse form. And maybe with number 6, you're inclined to do that, but I'm going to say, hey, don't do that. I want you to see that this is the integral of u prime over u, which is the natural log of u. Okay, so I'm going to point that out. In our denominator, I can make this substitution that 4x squared plus 3 is our u, and then the derivative of this is, what do you know, 8x dx. Okay, so here is our hook-on factor here. Here's u prime. So straightforward, this is the natural log of the absolute value of 3 plus 4x squared plus a constant. Now, you may see it too written like on answer keys like this, 3 plus 4x squared plus c. And you'll say, hey, Schwarberg, where did the absolute values go? Well, I mean, 4x squared plus 3, that can never be negative because we're squaring our variable. So even if it is a negative, it's always going to be positive. So if you see the absolute values go away, that's why. But they're both equivalent. Number 7. Now I have 8x squared. So if I did a u substitution with the denominator, it doesn't account for all of the x's in the numerator, and that's a problem. And so we're going to go ahead and go back to what we learned about at the beginning of this video, is that if the powers are the same between numerator and denominator, or if the numerator is greater than the power of the denominator, then we need to go ahead and do long division. So that's just what we will do. I'm going to go ahead and take 4x squared plus 3 and then divide this into 8x squared. So this happens 2 times. We get 8x squared plus 6. And change our signs. So I get a remainder of -6. Okay, so minus 6 over 4x squared plus 3. Okay, so let me rewrite this integral. So this is equal to 2 dx minus the integral of 6 over 4x squared plus 3 dx. Okay, and now I can go ahead. The first integral is very straightforward. I just have 2x. For this, the second integral, I'm going to go ahead and, well, this looks like tan inverse form. So I have a u that is 2x. I have the derivative of that is 2 du, or u prime. I've been calling it u prime, same thing. U prime, and then our a value is square root of 3. Okay, so notice I have a 6, so that accounts for the 2, and then I have a leftover 3. Okay, so this is minus 3 times the integral of 2 dx, right? There's your hook-on factor. And then I have the 2x squared plus root 3 squared. Okay, so let's finish this off. All right, so this is tan inverse form. Okay, so minus 3 times 1 over a, which is root 3, tan inverse of u over a. So 2x over root 3. Plus a constant because this is indefinite. All right, so and that one is similar again to example number 5 for that backend, okay? All right, last example of this long video. Here I am going to go ahead and integrate x plus 4 over 4 minus x squared dx. Now, if you're going to go ahead and try to integrate this, my first inclination is to let the denominator be equal to u. All of this I'm going to write, by the way, is wrong. So maybe you don't want to write this down. Maybe I'm kind of talking through my process here. I'm going to end up erasing this, heads up, okay? So 4 minus x squared is going to be u, and then du is equal to negative 2x. Now notice that this doesn't account for that, right? For my x plus 4. So, okay, this is not a good route to go. Well, one trick that we can do I want you to see that you have two terms in your numerator. And when you have two terms in your numerator, you can go ahead and split your integrand. So this is going to be the integral of x over the square root of 4 minus x squared dx plus the integral of 4 over the square root of 4 minus x squared dx. Now, why the heck would I go ahead and do that? Well, we've just seen some techniques where when we have a square root in the denominator, this can represent sine inverse form, but sine inverse form only has one term in the numerator, okay? So now that I've done this, let's go ahead and see, okay, does this kind of help at all right? So for our first integral here, I'm going to go ahead and I'm going to let u be equal to 4 minus x squared. And then the derivative of this is negative 2x dx, okay? And let me set this up. So this is the integral of 4 minus x squared to the power of negative 1/2. I'm bringing it up, okay, times x dx. And what I'm going to do is I'm going to introduce a negative 2 here and then balance it with a negative 1/2 in the front. Okay, and I'm just using power rule. That's power rule form, PR form, if you will. I'm going to change that negative 1/2 to a positive 1/2. Okay, so this gives us negative 1/2 times 4 minus x squared to the power of positive 1/2 now, right? And that negative 2x dx, there is our hook-on factor. Okay, and I have to divide by the new power, which is 1/2. Okay, and I'll go ahead, I'll clean that up in a bit. All right, now let's go ahead and go back up here. And for this integral, I have sine inverse form. Okay, so I have a u that is just x. That's nice and straightforward. I don't have to worry about du. And then I have an a value that is 2. Okay, so I have that 4 out front, which is, well, if I just rewrite it, 4 integral of 1 over 2 squared minus x squared dx. You should be able to see our integration rather easy. So plus 4 times sine inverse of x over 2 plus a constant. Okay, and again, that's similar to example number 1. So there you have it. I can go ahead in this form. I can cancel these two 1/2. I'm dividing and multiplying by it, or you can multiply by the reciprocal, right? 2 times negative 1/2. So our final answer, negative square root 4 minus x squared plus 4 sine inverse of x over 2 plus c. Okay. All right, here is a practice problem. Please go ahead, give this one a go. All right, hopefully you paused it. Here is the solution. Hopefully you noticed that the numerator is bigger than the denominator, so you're going to have to go ahead and do long division here. In this example, you kind of have multiple steps for long division. So when you go ahead and long divide, your quotient should be 2x minus 2 minus 2 over x plus 1. Okay, and there's the long division if you wanted to double check that. And this is now a rather straightforward integral here. So the integral of 2x is 2x squared divided by 2, which just gives you x squared. Integral of negative 2 dx is just negative 2x. And then the integral of -2 over x plus 1 is 2 times the natural log of the absolute value of x plus 1 plus c. All right. That's going to do it for this video. I'm going to go ahead and pick up and finish the rest of this lesson in another video. All right. Catch you next time. Peace.